Microgrids are localized energy systems designed to generate, distribute, and potentially store electricity for a defined area, such as a neighborhood, campus, military base, or industrial site. Though smaller in scale than conventional wide-area power grids, microgrids serve the same fundamental purpose, ensuring a reliable balance between electricity supply and demand in real time. Despite their size, microgrids are not a new concept. Historically, isolated systems serving small communities, islands, or private industrial plants operated independently, effectively functioning as microgrids long before the term became widespread. Over time, most of these standalone systems were interconnected to form regional or national power grids. Today, however, microgrids are experiencing a resurgence due to the increasing demand for resilient, cost-effective, and sustainable energy solutions. Microgrid definition and classification. A microgrid is defined as a localized network of electrical components comprising both power sources and loads managed by a single, centralized control system. This system can operate in sync with the main utility grid or function independently island mode, depending on technical and economic conditions. The shift from traditional centralized power systems toward microgrids is driven by several factors, including rising fuel costs, concerns about power quality and availability, infrastructure aging, vulnerability to natural disasters, lack of advanced control systems, and the growing impact of climate change. In response, microgrids have emerged as a modern, adaptable solution within the evolving energy landscape. Types and key drivers. Based on this definition, microgrids can generally be categorized into two primary configurations: on-grid and off-grid, each with two distinct subtypes. On-grid microgrids, these have access to the national grid or wholesale electricity markets and are further classified into, using existing utility lines, no control over the broader grid, using private infrastructure allowing for grid control and possible islanding operation. Off-grid microgrids. These operate independently without any connection to the national grid, typically deployed in remote or isolated regions such as mountainous areas or islands, developing or underserved regions with limited grid infrastructure. These different configurations result in varying key business drivers for deploying microgrids. Instead of trying to meet all possible goals, it's more effective to focus on the specific problem your market faces and how a microgrid can address it. The primary drivers include cost-effective energy pricing, improved resilience to grid outages or disruptions, reliable energy availability in underserved or remote locations. Off-grid microgrids, powering remote and isolated communities. The off-grid microgrids are typically deployed in locations where access to national or regional electricity networks is either physically impossible or economically unfeasible. This includes islands, remote communities, and isolated industrial operations such as mines or research stations. Islands and isolated communities. Many island communities operate their own independent grids. Traditionally, these systems relied heavily on diesel or heavy fuel oil generators due to the ease of fuel transport and storage. However, fuel costs, logistical challenges, and environmental concerns have prompted a shift towards renewable integration. Although islands possess ample wind and solar resources, integrating intermittent renewables poses operational challenges. Unlike diesel generators, which can be dispatched on demand to match load variations, wind and solar generation depend on weather conditions. Sudden changes in sunlight or wind intensity can cause fluctuations in output, necessitating fast response backup systems and advanced control mechanisms. Until recently, such sophisticated controls and power electronics were unaffordable or impractical for small island systems. Today, modern microgrid technologies including advanced supervisory control systems and stationary energy storage enable much smoother integration of renewables. This not only reduces fuel dependency and operational costs but also minimizes environmental impact, enhances reliability, and improves overall efficiency. A real-world example is Calvert Island in British Columbia, Canada, where a modernized microgrid was implemented with support from Cummins to enhance power reliability and reduce fossil fuel reliance. Remote industrial sites. Similar challenges exist in remote mainland locations such as northern Canada and Siberia. Industrial operations like mining sites require substantial energy and cannot rely on distant grids. Transporting liquid fuels across harsh or inaccessible terrain is costly and logistically complex. Consequently, there is a growing trend toward renewable energy integration in these microgrids, complemented by control systems and storage solutions. Some operations even explore producing synthetic fuels on site using renewable electricity. Microgrid classification by application. Microgrids can be grouped into several categories based on their application areas. The 5 primary types are military microgrids, designed for use in military bases or field camps. These microgrids usually operate autonomously. They typically rely on diesel generators but are increasingly incorporating renewable energy sources for hybrid operation. Campus microgrids. These serve educational institutions or corporate campuses. They often integrate combined heat and power CHP systems to supply electricity and thermal energy efficiently. Community microgrids, used in both developing and developed regions. In emerging markets, they provide first-time electrification, while in developed regions, they support community-level renewable energy adoption and resilience. Island microgrids, completely isolated from the main grid, these microgrids operate independently. Their reliance on renewable energy is growing due to economic and sustainability advantages. Commercial and industrial CNI microgrids, these systems support facilities like factories, hospitals, and industrial plants. Often capable of operating both grid-connected and independently, they provide reliable power tailored to critical loads. Microgrid classification by power supply configuration. In terms of how they are connected to power sources, microgrids can generally be classified into 3 types: grid-connected microgrids, off-grid island microgrids, hybrid systems capable of switching between connected and island modes. Microgrid classification by structural design. According to their construction and power conversion methods, microgrids can be divided into 2 main types: single-stage power conversion microgrid. These systems operate either entirely on AC or DC power, without the need for conversion between the two. Their simplicity makes them suitable for smaller or more uniform energy setups. Two-stage power conversion microgrid, used primarily with renewable energy sources like solar PV and wind. These systems convert DC output from renewables to AC using power electronic converters to match grid or load requirements, enabling better power extraction and integration. Microgrid classification by control strategy. Microgrids can also be classified based on their control mechanisms, which determine how energy generation, distribution, and load management are coordinated. The 2 main types include centralized control microgrids. A single controller manages all decisions and operations across the system. Decentralized distributed control microgrids. Multiple controllers operate semi-independently, enhancing system resilience and flexibility. Power export from photovoltaic, PV systems to the main grid. Photovoltaic systems have become one of the most widely adopted distributed energy resources in today's modern power grids. Due to the significant decline in PV system costs, adoption has rapidly expanded from residential rooftops to large-scale utility installations. Increasingly, small-scale grid-connected setups such as microgrids, homes, commercial, and industrial buildings are using PV systems to generate electricity. This allows for greater self-consumption, leading to reduced electricity bills, and enables the export of surplus energy to the main grid for additional financial return. However, many countries and regions impose limits on how much electricity can be exported from PV systems to the main grid. For instance, in Australia, the ASNSC standard limits single-phase residential PV systems to export no more than 5 kilowatts of surplus electricity. For 3-phase connections, the export limit increases to 30 kilowatts. In Western Australia, the limits are slightly different: 5 kilowatts for single-phase and 15 kilowatts for 3-phase connections. To enable and track energy exports, an additional digital metering system is required, which typically costs around $500. Exporting energy during peak hours can be financially advantageous. For example, in the United States, the average cost of PV-generated electricity is about 6 cents per kilowatt-hour during standard periods, but it can increase to 9 cents per kilowatt-hour during peak export periods. Germany is a leading example of PV integration, with over 1 million PV systems connected to the main grid. There, individual PV systems can have capacities up to 30 kilowatts, and up to 70% of the electricity generated can be exported to the grid. Overall, the global integration of PV systems into the grid continues to rise steadily. Grid-connected microgrids, enhancing reliability in developed areas, even in fully electrified urban and industrial settings. grid-connected microgrids are gaining popularity. Organizations invest in these systems for two key reasons: resilience and cost efficiency. Enhancing reliability and energy security, power outages can have severe consequences for facilities with critical operations. While homeowners may use portable generators, complex institutions like military bases, airports, hospitals, and data centers require a more advanced solution. A microgrid ensures continuous operation by seamlessly integrating multiple energy sources, backup generators, renewable energy, and storage into a coordinated system. These systems can continue to operate in island mode during grid outages, maintaining power to essential loads. Reducing costs and managing power more efficiently, grid-connected microgrids allow facilities to centralize their power generation and consumption internally, often behind a single utility meter. This enables the deployment of solar arrays, wind turbines, battery storage, and regenerative technologies without direct interference from the utility. For example, ports use regenerative cranes that generate electricity when lowering cargo. Connecting such equipment directly to the utility grid can be complex or even restricted. Through a microgrid, operators can recycle power internally. Cranes generating electricity can supply power to others lifting cargo. This results in significant utility cost savings. Why microgrids are essential today: sustainability. Microgrids offer an ideal platform to incorporate renewable energy resources such as solar and wind, enabling organizations to reduce their carbon footprint. Intelligent microgrid controls ensure efficient use of these resources, despite their intermittent nature. Economics. Microgrids can help reduce electricity costs by dynamically selecting the most cost-effective power source. They also help organizations participate in demand-side management programs, optimize generator usage, and minimize demand charges. Resilience. In both on-grid and off-grid scenarios, microgrids provide enhanced resilience by offering redundant power sources. In the event of a utility failure or fuel shortage, microgrids can isolate themselves and continue to operate independently using local generation and storage. How do microgrids work? The backbone of a microgrid is its intelligent control and energy management system. These systems monitor real-time energy demand and make decisions on how to meet that demand using various distributed energy resources (DERs). They evaluate multiple factors: cost, weather conditions, resource availability, and load profiles to determine optimal dispatch strategies. A typical microgrid may include solar PV panels, wind turbines, diesel or gas generators, energy storage systems, batteries, power conversion and control equipment. The intelligent control software orchestrates the operation of these components to maintain power quality, ensure reliability, and minimize cost. Key differences between microgrids and centralized grids. The primary distinctions between microgrids and traditional centralized generation can be summarized in two terms: proximity and resilience. Proximity. Microgrids generate electricity near the point of consumption, reducing transmission losses and infrastructure costs. Centralized grids, by contrast, transport electricity over long distances from large-scale power plants. Resilience. Microgrids are designed with multiple energy sources and failover capabilities. They can isolate from the central grid during disturbances, continuing to power local loads. Centralized systems, however, can experience widespread blackouts if a major plant or transmission line fails.